all of you. In the morning session, we were discussing about Cantor theorem in our post-procedure analysis, but due to some internet connection issue, the presentation was not so good, and we were not able to discuss it properly. So now we are going to discuss it again in this lecture. So let us start about Cantor's theorem. So again repeat that please do not misunderstood with Cantor set, because there is one terminology known as Cantor set also in data analysis. We will discuss it in the coming lectures of our core course. So Cantor's theorem says that there does not exist any objective map from a set onto its power set. That is, if P is any map from S to power set of S, then P can never be on P. So let us first discuss about its application. Assuming that this result is true, its application is power set of natural number is not countable. Why we can say that? Because in our lectures we have discussed that if a set, in order to prove a set to be countable, we need to define a surjective map from N onto S, right? So let me write it. In order to prove a set S is countable, okay, let me use S delta is countable, there must exist a surjective map from set of natural number onto S delta, right? So if P of natural number, power set of natural number is countable, then there will exist an onto map from N onto power set of N. That means contradiction to Cantor's theorem. This implies power set of natural number is not countable or uncountable. And so this is one of the results which has often been asked in various competitive examination, be it IIT-JAM or GATE or even CSIR-NET. They will give you 4 options saying, say, N cross N is countable, power set of N is countable, power set of N is uncountable. And in the options, they will say that A and B are true, A and C are true, and in this manner, they frame some questions in the competitive examination. So, in order to cram power set of N is uncountable, you might forget it. But if you know your Cantor theorem, then it is very tricky. So let us proceed to the proof of Cantor's theorem. Proof of Cantor theorem. That S be any set and PS be power set of S. Power set of S. And let, if possible, P is a map from S to power set of S such that P is onto. So what are we doing? We have assumed that there exists an onto map from S to power set of S, and we will prove that we will reach to a contradiction, right? And if we reach to a contradiction, then our assumption is wrong, and there cannot be any onto map. So this is the idea. So we know that power set of S contain subsets of set S. First of all, we need to remember that. Now, define a subset D is equal to set of all those A in S such that A does not belong to P of A. Fine. So D is a subset of S. This implies D belongs to power set of S. Fine. This implies there exists some A naught belongs to S such that D is equal to P of A naught. Fine. Why can we say that D is a subset of S? This implies D is in power set. So D is in the range. If D is in the range, then since we don't do, there will exist a map. There will exist some element A naught such that P of A naught is equal to D. Now P of A naught is equal to D, which is set of all those A in S, such that A does not belong to P of A. Now A naught belongs to S. This implies either A naught belongs to D or A naught doesn't belong to D. Yes, one. Yes, one. A naught belongs to D. This implies A naught belongs to S and A naught does not belong to phi of A naught. This is the definition of D. Phi of A naught, which is equal to D. This implies A naught does not belong to D. We started with A naught belongs to D and we reached to A naught does not belong to D. Hence contradiction. Hence we reached to a contradiction. Case 2, A naught, we have discussed. Case 1, A naught belongs to D. Let us take A naught does not belong to D. A naught does not belong to D. This implies A naught belongs to set S and A naught belongs to phi of A naught, right? Phi of A naught is D. This implies A naught belongs to D. We started with A naught does not belong to D. We reached at A naught belongs to D. We reached to a contradiction. In other cases, hence our assumption is wrong. And hence there does not exist any onto map, any surjective map from S onto power set of S. Fine. What we have discussed till now. First, definition of countable and uncountable sets. Second, set of natural number. It is the definition. So set of integers, set of rationals, n cross n is countable. Third, countable union of countable sets is countable. Fourth, Cantor's theorem. Fifth, Crowley, that our set of natural number is uncountable. This much we have discussed till now. In the next lecture, we will discuss algebras and order properties. Or we will take on some inequalities on R. For example, random inequality. So all of these things can be referred to chapter 2 of book 1, which we recommended. That is Introduction to Real Analysis by Bartlett. Fine. So with this note, we will end our today's lecture.